So hi everyone. I will record videos and upload them to Learn. You can find the videos in weekly content on Learn. And also I will be doing my office hours on Fridays at between 5 p.m. and 7 p.m. So you can ask your questions there. And also you can send me emails, of course, to ask your questions. Okay, so let's start. So the first question is about translation statement, the given statement into English. So remark that the domain is real numbers, right? Let me change the color. So the domain is real numbers. It means X and Y can take values from real numbers. So what does it say? It says for all X, there exists Y, X is less than Y. So what's the translation? It means for any real number X, okay, as the domain is real numbers, for any real number X, there exists some real number Y. Y it's also a real number because the domain is the real numbers. So the Y that will be found should be in real numbers, okay? So for any real number X, there exists some real number Y such that they satisfy this inequality. X is less than Y, okay? Let's give some example. So this means this for all X means that you can pick any real number for X, right? Let's pick X equals to 5. Okay, let me change the color, sorry. So let's pick X equals to 5. Okay, this is a real number, so we can pick this. So what about Y? We don't know yet, okay? We don't know if it exists or not. So, but we need to, at the end, we need to obtain this if such Y exists, okay? So, is there any Y which satisfies this? Yes, for example, we can pick 5.01 or 5.3 or 6 or 1,000, right? Any of these are real numbers. So we can say that for X equals to 5, we can find some real number which is greater than that, okay? So this means that. So it means that actually for any real number, you can find some real number, some another real number such that the first one is less than the second one. Okay, it says this. It's always correct in real numbers, right? So what about the second one? So here we say, or we can translate it as for any real number X and also for any real number Y, if X is greater than or equal to 0 and, this means and, Y is greater than or equal to 0, then X times Y, the multiplication of these two values, is greater than or equal to 0, okay? So we can also pick some number for X and for Y, and with this condition, of course, right? We can pick X equals to 2 and Y equals to, for example, 0, right? We are able to choose that because we have equality here. Then what happens? X times Y, which is 0 obviously, is greater than or equal to 0, right? So we can pass to the third part. So here we have for any X, for any Y, right? For any real numbers X and Y, there exists some real number Z, right? Here, X times Y equals to Z, okay? So for any real numbers x and y, let's pick x equals to, for example, x equals to 2 and y equals to 3. So x times y equals to 6, which is z. So there exists some z, right? This is also correct in real numbers. So these were the simple examples. So let's see the second one. Now we'll determine the truth, okay, the truth value of the statements. So let's start with this. Again, the domain is real numbers. It means you can pick the values for the variables here from real numbers. So for that, of course, we will determine the truth value, okay? We will determine if it's true or not. So for any real number x, does there exist a real number y such that x squared equals to y? It is correct, because if you pick any real number for x, its squared will be again some real number, right? For example, we can pick here x equals to I don't know, -1, right? Then -1 squared equals to 1, which is again some real number, right? It's in real numbers. Any of these x, any of these real numbers, its squared will be exist and it will be in real numbers, so it is correct. Okay, so what about this? It says for all x, for any real number, there exists some y such that x equals to y squared. So for example, if x equals to 2, or let's start with some basic number 4, okay, then we obtain here 4 equals to y squared, right? We'll check if this exists or not. So this equation gives y is either -2 or +2, right? So such y exists, right? But what if x was -1? Then we again obtain -1 is equal to y squared. But this equality is not correct in real numbers, right? Here it gives that y is square root of -1, which is I, which is in, again, the complex numbers, right? Not in the real numbers. But our domain is real numbers, so this is false. Okay, this is not correct. This statement is not correct. It is sometimes correct, but it's not correct for any x, so it is false, okay? If there is at least one value which does not satisfy this equality, then the statement is false, okay? So what about D? We see for any x and for any y, for any real numbers x and y, x plus y is not equal to y plus x. So, for example, let's take x equals to 4 and y equals to 1. What happens then? So 4 plus 1, x plus 1 equals to 5, which is also 1 plus 4. So we found right here two values which does not satisfy this inequality. Then this statement is false, okay? And now we have this part. There exists some x and there exists some y such that they give these equations, okay, at the same time, because we have here and. So if such x and y existed, right, then we would have these two equations as in here. So if you multiply by -2 by the third equation, we obtain -2x minus 4y equals to -4. So if we add these two equations, we'll obtain 0 equals to +1, right? Which is not correct, obviously. So there is no x and y. There is no such x and y in the real numbers, of course. That the statement is false. So what about the third question? So we will find the negations of the statements. What about this one? So remember that if we have some prepositions P and Q, okay, we have such preposition, its negation is equivalent to this, not P or not Q. So we do the same thing actually here. So what's the negation of this? It's for all x, okay? So the negation of this is for all x, and of course the negation of this, there exists some y, it means the negation is for all y, okay? So again, the negation of this predicate is not, this is not P. Now what happened to this? It will be or, as in here, okay? So there exists some x, there exists some y, and not q, okay, as in here. So this one was again easy. So we will here find a counterexample. So it means we will find values, some values, which will not satisfy the statement, okay? So you don't have to write this actually, but I wanted to be clear. So if we can find some x and y which does not satisfy this inequality, then we would be done. So what's the negation of this statement? It's obviously there exists some x, there exists some y, x, y is less than x, right? The negation of this is this. So if we will find some, if we can find some x and y which does not satisfy this inequality, then they should be satisfying this inequality. Okay, so we can either find some values which satisfy this or which does not satisfy this, okay? So we can pick any of two variables. Here, remark that the domain is integers, okay? The integers. Okay, we write it like this. So we can choose x equals to 1 and y equals to -1. What happens then? So we need to check this part. xy is, obviously, it's -1, which is less than 1, right? -1 is less than 1. So they satisfy this. It means these values are counterexample for this, okay? Or you can either check, as in here, xy is -1, which is not greater than or equal to 1, right? This is not correct. So they are counterexample for this statement, okay? Okay, now what do we do here? So for each argument, we'll check if it's correct or not correct, okay, or incorrect. So what does this say? It says if somebody enrolled in the university, okay, as in this statement, if somebody is enrolled in the university, then he or she should live in a dormitory, okay? So we have here let's say this is the statement P. We have P implies Q, okay? And Q here means living in a dormitory. It says P implies Q. So it is equivalent to say this, which is not Q implies not P, okay? In English, it means, so if somebody doesn't live in a dormitory, then it's he or she is not enrolled in the university. So we can, if we know this, which we know obviously from this second phrase, Mia has never lived in a dormitory. So we have this, right? Not Q, which means if somebody doesn't live in a dormitory, we know Mia has never lived in a dormitory. Therefore, we can obtain this, which is Mia is not enrolled in the university. So the argument here is correct. What about the second one? Here we have this, a convertible car is fun to drive, okay? We know this, we assume this phrase, okay? If some car, if any car, if a car is convertible, then it's fun to drive it, okay? We know this, okay? We assume it. So we have P here, which is a car is convertible, and Q here, which is it's fun to drive, okay? So we know Isaac's car is not convertible, right? We know not P. We know only not P, okay? So remember that this truth table, okay? If we have here P, the values of P, and the truth values of Q, we know this. So we know not P, right? Not P means a car is not invertible. A car is not, convertible. So we know Isaac's car is not convertible. We have this, right? Or this. So the conclusion, Q is not important. The statement is correct in any way. So therefore, we cannot say Isaac's car is not fun to drive. We don't know the truth. Actually, we have a false assumption. That's why we cannot obtain if it's correct or not correct, okay? This conclusion, I mean, Isaac's car is not fun to drive. If Isaac's car was convertible, then we know that it's fun to drive. But if it's not, as in here, we're not able to say anything. So this is incorrect, okay? Thus the argument is not correct. Now we have this question. We know n is an integer, okay? It's in Z. N is in Z, okay? We want to show this. So what's P in here? It's this, okay? We want to show this. So if this is correct, it means we need to assume this, then this should be correct. It means we need to show this. So we assume that n to the 3 plus 5 is odd. Now what do we do? We need to show n is even. Now since 5 is odd, it's an odd number, then as this is odd, then n to the 3 should be even, right? So its factors should be even. One of these factors, its factors should be even. So, but we also know that any of its factor is n, so n should be even, okay? We know this is odd and this is odd, so n to the 3 should be even. which means at least one of its factors, should be even, but n to the 3 equals to n times n, right? So one of these, its factors is obtained by n, right? Formed by n, right? All its factors is n, so n should be even. So what about this question? Now again, we assume here n is a positive integer. Now we assume n is an integer and it's greater than 0. Now we want to prove that n is even if and only if 7n plus 4 is even, okay? So here we have the statement n is even. So we have the statement P. And we have if and only if. We have another statement which is 7n plus 4 is even, okay? So P is n is even, Q is 7n plus 4 is even. Now, how do we show such statements? We need to show this. First, we assume P and show Q, and also then we assume Q and show P, okay? So here in the first paragraph, I assumed that n is even, okay? I assumed P here. So I assumed P, n is even, and we will show Q, which is 7n plus 4 is also even. Now we know n is even by assumption here. Then so is 7n, right? If n is even, then it's also even. Now we add another even number to this even number, okay, and obtain 7n plus 4. We have two even numbers and their sum, so it will be again an even number. Thus we showed Q here, which is 7n plus 4 is even. Now what do? We'll show this part. We assume Q now, which is 7n plus 4 is even. Now we show P, which is n is even. Okay, P here, Q here. We assume this. Again, if it's even, by assumption we know it, and as 4 is even, then this should be even. And it's clear that 7 is odd, and this number is even, then n should be an even number. So we showed this part, we showed P. Okay, first we showed this, and then this, hence we showed that this equivalence, okay, of the statements. So we're done. I'm passing this question because it's so easy and can take the values from this as it's positive integer. It can be 1, 2, 3, and 4. So you can plug them into this inequality and you'll see that. So it's easy. I'm passing it. What about 9? So here we need to show that there are no solutions for x and y for this equation. Okay, we have this equation 2x squared plus 5y squared equals to 14. Now we know these variables are in z, they are integers. And remark that if y is greater than or equal to 2, or y is less than or equal to -2, its squared should be greater than or equal to 4, right? If we have these two conditions, we have this. If we multiply this by 5, we get this inequality. 5y squared is greater than or equal to 20. But we see that this equality on the right side of the equality, we have 14. So we cannot have this 20 here. So it means y is in between -2 and 2. Because if it's greater than this value or less than this value, we obtain this, which contradicts the right side of the equality. So y should be in this interval. As it's an integer, okay, as it can take the values from integers, it may be -1, 0, or 1. Okay, there are 3 values for y that it can take, sorry. Now, what happens if it takes these values? We will examine the cases, okay? So what are the cases? If y equals to -1, if y equals to 0, and if y equals to 1. So we examine these cases. So first case, I examined these 2 cases in the first case because they give the same consequences. That's why I examined them in this case. So if y equals to -1 or 1, then we have 5y squared equals to 5, right? If y equals to these 2 values, we have here 5. And then this equality gives that 2x squared equals to 9. But we know 9 is odd and 2x squared is even. Thus, this equality has no solution. Okay, so in this case, we cannot find any of solutions, any of integers to the solution, this equation. Now, the second case is y equals to 0. Now, what happens? We know if y equals to 0, 5y equals y squared is 0. So we get 2x squared equals to 14, which gives x squared equals to 5. But we know x is in z, right? Thus, there is no solution for that either, okay? In both cases, we cannot find any solution. And as there is no other cases, we can obtain that there are no solution in integers to this equation. This is the last question. So we'll prove there are infinitely many solutions, okay, in positive integers to this equation. So there is a hint here. We'll use that, but there was a typo in the worksheet, so it should be m squared minus n squared, but in the worksheet it says m squared times n squared. Okay, it's right. That was wrong. It should be m squared minus n squared. So we'll use this. Okay, as there it says that m and n are integers. There's no bound for them, so they can any value from integers. That's why we say let m and n be arbitrary integers. Okay, there is no limit for that. Okay, so they are integers. There are some integers, and we say let x to be this, y to be this, and z be this. So what do? We need to show this equality. So if you want to show some equality, you should either start from the left side of the equality and obtain the right, or you can do the opposite, or you can show the difference between them is 0. Okay, you can do whatever you want of these 3 ways. So I started from the left side and obtained the right one. So x squared plus y squared equals to this. We know these equalities, so we plug them into the equation and we made some operations and get this. M squared plus n squared is z squared. So we started from the left side of the equality, here the left side, and right side of the equality. Here we have the right side. As m and n were arbitrary, right? There is no bound for them. then it means this x, y, and z be any integer by up to the choosing the choices for m and n. Okay, so as there was no limits for that, for them, m and n. So it means there are infinitely many solutions for this question, because we can pick any m and n to get x, y, and z, right? That's why there are infinitely many solutions for x squared plus y squared equals to z squared. So that was the last question of the worksheet. Again, as I said before, you can attend my office hours, or you can send me emails to ask your questions. See you next week.